Hi, my name is David Morris, and we are doing problem number 21. And as you can read here, we have the semicircle with charge Q positive, and a rod with length L, which is positive Q as well. So first of all, we need to get our basic equations, like the point charges along this semicircle would be dx equals r d theta, where dx is just the length of a random point, and r is the radius, and d theta would be the change in the angle. And since starting angle is 0, ending angle is pi, just write down 0 to pi. And then the charge per length of the semicircle would be q over pi r. Since the length of an entire circle would be 2 pi r, the circumference, we're just doing a semicircle, so it's just going to be pi r. And then the charge per length on the rod, we just put rod there, is q over L, since it has a length of L. And we're going to put just S for semicircle. And the change in voltage, or dV, is going to be equal to Coulomb's constant times the integral of 0 to pi, those are our bounds because that's where it ends and begins, of lambda dx over r. And this is the semicircle lambda. And then we can just set this equal to Coulomb's, so it's r d theta over r. Then we can cancel out the r's because we have them on the top and bottom. And then the integral just turns into ke 0 to pi lambda d theta.
Hi, my name is Jake Blatz, and I'll be telling you how to solve for the rod. So first, in the given equation, we have the length of the rod is equal to 2r, and so we can simplify that as our bounds. Dividing it by 2, we have negative L over 2 to L over 2. And we want to be solving for the voltage. So we have the voltage is equal to Coulomb's constant, dq over r. And then substituting into the variables, we have lambda, the entire charge, dx over the magnitude of the distance, which is equal to x squared plus y squared, and that's the distance from the origin. And so substituting that in further, we have dv is equal to Coulomb's constant. We can take the constant out of the integral, so our bounds being L over 2, negative L over 2. We have lambda dx over the magnitude again, x squared plus y squared. Simplifying this further, we can take the other constant out, lambda. We have negative L over 2 to L over 2 dx over the magnitude.
Hi, my name is Jason Cruz, and I will continue on with the problem by integrating what we have here. So I've already written down all the work, and I'll just take you step by step. So what we have here for the integration of the semicircle, we have the ke times the lambda of the semicircle of the integral from 0 to pi of d theta, plus the ke times the lambda of the rod of the integral from negative L over 2 to L over 2 of dx over the square root of x squared plus y squared. And then once we integrate that, the integration for the semicircle is easy enough. So what we're given here is ke times the lambda of the semicircle times pi minus 0. Whereas for the rod, I found this integration formula on, I believe it was worksheet number 5 that we were doing. So what we're given with is the natural log of x plus the square root of x squared plus r squared from the integral of negative L over 2 to L over 2. And then from there, you just plug some numbers in. So right here, for the semicircle, you're left with just pi, since 0 times ke and lambda is 0. And for over here, we could leave the ke times lambda on the side, and then we just plug in the L over 2 plus the square root of L over 2 squared plus r squared minus the natural log of negative L over 2 plus the square root of negative L over 2 squared plus r squared. So yeah.